Hello everybody and welcome back to this video. In this video we'll be looking at Theorem 2.4.2. We'll be looking at how composition of linear transformation translates to product in the matrix side, on the matrix side. All right, so let's say I have three finite dimensional vector spaces, U, V, and W. And let's say I have a basis, BU for U, BV for V, and BW for W. All right, if I have two maps, one from U to V, one from V to W, then I can compose them. And I can ask what the matrix of that composition is. To determine that, I would first look at this map, and what we'll show first is that this is T2. You could look at the representation of T2 in, this is from V to W, so BV, BW. This representation on Euclidean space and compose it with a representation of T1. T1 is from U to V, so I'm going to use BU and BV to match it to a map in Euclidean spaces. All right, so the Euclidean equivalent of T2 composed with T1 is the composition of the equivalent of both maps separately. That will mean that if I look at the matrix of T2 composed with T1, I'm going to get the matrix of T2 times, this is matrix multiplication, the matrix of T1. All right, then a linear transformation, T from U to V, is an isomorphism if and only if. Here, missing the matrix, but you have it in your note. The matrix of T is invertible. And then the inverse map would correspond to the inverse of the matrix. All right, so we want to prove this. This is a bit abstract. I mean, it's very helpful because we could relate everything to matrices and play with matrices. So once we have this, we'll be happy, but we still need to prove it. All right, so I'm going to start with this result here. I'm going to look at T2 composed with T1. All right, so I'm just going to use the definition to write out what this map is. All right, so I have a diagram underneath here to help us follow because this is a bit confusing. All right, so I want T1 composed with T2. So T1 composed with T2 is this one. This is T1, this is T2. All right, so if I want the map corresponding to it on Euclidean space, I'm going to take this map, which is LBU. Let me label it for good. I'm going to take this map, then T2 composed with T1, and then this map back. So this one was the coordinate map for W. All right, so this is, let me write it out, C first, L, C, BW, and then T2 composed with T1, and then L, BU. All right, so that represents blup, blup, blup. Now, what I'll do is I'll take a little stop in between. I'll do this and then come back and do this. And that's going to be the same because these two maps are inverses, so they cancel. Right, so what I'll do is I'll do CBW composed with T2, and then I'm going to insert the two inverses, LBV, CBV, composed with T1, composed with LBU. All right, so really duck, 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 duck. Now, this part here, that's the map corresponding to T2, and this one is the map corresponding to T1. So what I get is T2 BV BW composed with T1, if I split it this way, BV, BU BV, sorry. All right, so that proves the first result, this one. It wasn't so bad, it's just that there's so many different letters floating around that without the diagram, I would have gotten lost. And then we're just going to use proposition. We've already proven these results for Euclidean space, and now this is all in Euclidean space. And so the matrix of T2 composed with T1, BU, BW, that's the same thing as the matrix of the Euclidean map. And so we just saw that that was T2 and T1 Euclideanized separately. I like that verb. Euclideanized. All right, and then this is where proposition applies. If we have a composition of Euclidean map, then the matrix of the composition is the product of the matrices. All right, so since it was true for the Euclidean maps, it will be true. Sorry, I'm getting my indices wrong. So this one's V. So T2 is from V to W, and T1 is from U to V. All right, and this is what we wanted. All right, so that shows this one and this one. So we're done with one. Now we're going to move on to two. I'm going to assume that the linear transform should an isomorphism and prove that the matrix is invertible and vice versa. All right, so assume that it's invertible, that T is invertible. So that means I have a diagram again. So here's T. I'm assuming that T is invertible. So I have T inverse here. Actually, I have it here, T inverse. All right, so if I assume that T is invertible, then I want to show that this map here is also invertible. Let's spell it out. The map T, BU, BV will take this map, then this, then come back. All right, so that's going to be LBU composed with T, composed with CBV. All right, but this is invertible, this is invertible, and this is invertible. And so this one is invertible with, and we know how to find this inverse. The inverse, I'm going to write it as the inverse of this, and then we'll bring the inverse in, and we'll get LBV inverse, T inverse, and then CBV inverse. But we know the inverse of LBV, and we know LBU, sorry. And we know the inverse of CBV. They're the coordinate maps for U and the linear combination maps for V. And so this is BUBV. And so if T is invertible, we just proved that if I look at the matrix, then that's going to be the matrix of this Euclidean map. But that Euclidean map is the same as this one, and then we land on an inverse of an Euclidean map, which we've already handled in that proposition. And so that's T, BU, BV, inverse. All right, so let's look at what we've proven. We're not done. What did we prove? We proved that if T is an isomorphism, then the matrix is invertible, and then the inverse is this. Okay, so now assume, right here. So if I assume that T, BU, BV, that the matrix is invertible, sorry, this is outside. If I assume that the matrix is invertible, well then, by the same proposition, so it's proposition 2.3.2, sorry. T, BU, BV is invertible. And so let me write, right? So usually we write T, BU, BV in terms of T, but we could do the other way around, right? So here's T, BU, BV. If I want to look at T, I could write it like this. And so as long as one of them is invertible, the other one will be, because these are pretty much equivalences. All right, so T is, so let's see from the diagram, this is going to be CBU, and then this is going to be LBV. So it's going to be CBU, T, BU, BV, L, BV. So this one is also invertible. All right, and in fact, if you want to know what the inverse is, you just have to look at the second. This is T, this is its Euclidean version, this is T inverse, this is the Euclidean version. These two are inverses, these two are inverses. Okay, so everything that happens on a vector space, you have exactly the same picture on the Euclideanized version, and you have exactly the same picture in the matrices as well. Right, so that's what you have to remember. The rest is a lot of notation, but really the idea is we get an exact picture on the matrix side, and so we can use matrices to solve a lot of problems, which we're happy about.